PhD at the University of Maryland with Van Luzu, and he's been working on basically the ways how we can get rid of carbon from the atmosphere due to carbonation of olivine. And he will talk more about his PhD work now. And he will come as a postdoc to my group to work on the carbon sequestration problem in spring or summer this year. So, welcome.
All right. Thanks, Matej, for the introduction. And I'd like to thank everybody for showing up and for having me here. So today, I'll be talking about the study on porosity generation processes during the olivine carbonation. This is part of my PhD work with collaborations from University of Edinburgh, and is funded by the Department of Energy and the National Science Foundation. So the last century has witnessed a significant change in the global temperature. Here showing two pictures of the global temperature variation comparing to a 5-year average. And here we see that 2017 shows a clear warming trend compared to back in 1884, while most of the area on Earth are still cooler than the average. So here is a report released by NASA and NOAA this Wednesday, showing that a consecutive year of record breaking in the global temperature, and 2018 was ranked the 4th warmest year from all the observation. And so this shows a long-term warming trend. And if we take a look at the CO2 concentration in the atmosphere, and we can see a strong correlation with the global temperature. Basically, the CO2 concentration in the atmosphere increases significantly since the Industrial Revolution. And then facing this problem, the Paris Agreement was adopted by consensus by 195 states and the European Union in 2015, trying to reduce emission as part of the method for reducing the greenhouse gas. And the aim for Paris Agreement is to hold the increase in the global average temperature to well below 2 degrees Celsius above the pre-industrial level. However, if we look at the projection of the current prediction, the global temperature is going to be increased by about 4.5 degrees Celsius at the end of this century. And studies have shown that to achieve the aim set by Paris Agreement, the emission must peak within the next decade and then decline to net zero by the end of the century. So apart from reducing the emission, what else can we do? The geoscientist has proposed the idea of CO2 sequestration. Basically, there are several ways to achieve this, either by injecting the CO2 into the reservoir rocks with low permeability caprock, so basically store the CO2 away in these reservoirs. Or we can dissolve the CO2 in saline water. And another solution to this is called the CO2 mineralization. Basically, the principal idea is to inject the CO2 into depths exceeding about 800 meters and react those with silicate to form the solid carbonate minerals. Here's one of the reaction equations. Basically, the magnesium-rich olivine react with CO2 to form magnesite and quartz. And because the CO2 here is converted to a solid mineral due to the reaction, it is considered a permanent secure solution to the high CO2 concentration in the atmosphere. And because of the high magnesium content in the olivine-bearing mafic and ultramafic rocks, and they are considered a great feedstock for this purpose. However, using the ultramafic and mafic rock as the feedstocks for CO2 sequestration remains controversial. This is because if we think about the reaction, generally, the reaction will lead to about 44% solid volume increase. So meaning that the precipitation of reaction product will fill out the pore space and cover the reaction surface, leads to a reduction of fresh reaction surface and also reduce the fluid supply because a decrease in the porosity and a lowered permeability. And as we know, the reaction surface and the continuous fluid access will be important for maintaining any reaction progress. So generally, this process is considered self-limiting. However, if we take a look at the natural outcrops, here's one of the outcrops in Norway, where we can see that natural carbonation of mafic and ultramafic rock can proceed to completion. Here, the peridotite has been fully weathered into magnesite and quartz. And commonly on these mafic and ultramafic outcrops that go through the carbonation, we always observe these fracture networks. And this is one of the examples in Oman, where we see loads of exposure of the ultralight. And here we see a complex network of fracture, which is clearly related to this carbonation reaction. So people have proposed the idea that with the precipitation of a reaction product, it could actually exert pressure around the growing crystal and eventually fracture the rock by when the pressure exceeds the local minimum principal stress. So the pressure is induced by crystallization, and prediction on these pressure are based on this equation, where the G stands for the Gibbs free energy change for a specific precipitation reaction, and then the delta V is the difference between the solid volume between the product and the reactant. And based on a study by Kellerman and Hertz, the olivine carbonation reaction is predicted to produce about couple hundreds MPa to GPa scale crystallization pressure. However, if we take a look at the laboratory study, we have not yet found such presence of such high pressure. So this leads to the question that we have, which motivate our study. Basically, is a carbonation reaction really a self-limiting process? If not, how is the fluid access maintained during the reaction? And does the reaction-induced fracturing account for maintaining the fluid pathway? If so, what's the mechanism for these fracturing? So in this study, we used a synthetic sample of olivine aggregate. Here, basically, we press the sample, press the olivine grains into this cylinder, and then we drill the hole and fill it with loose olivine sand that's coarser with a grain size of 200 to 500 microns. And then these containers are either made of 5 micron grains or 80 micron grains, so referred to as a small grain container and large grain container in the following discussion. And the whole sample is reacted with carbon-rich fluid at 200 degrees Celsius with at pressure condition of 15 MPa confinement and 30 MPa pore fluid pressure. And also in the study, we adopted the synchrotron-based X-ray tomography as one of the non-destructive detection techniques. This allows us to obtain a radiographic image of the reactor at any time without interrupting the reaction. And radiographic scans are collected every 30 minutes. So here, the sample sits on this rotating stage while the radiographic image are taken from different angles, and eventually by rotating the sample for 180 degrees, we will construct a 3D image of the whole sample. And then by collecting all the 3D data of the reactor at different time step and add time as the fourth dimension, we will have the so-called the 4-dimensional data we use for later detailed inspection. And then for the X-ray tomography, because each reaction phase would have a different density, and that would lead to a material-specific X-ray attenuation coefficient, which would result in a characteristic gray value in the acquired image. So put it simple, each reaction phase would have a different color in the image so that you can tell the difference. And our analysis are based on, are conducted in these three ways. So because each phase has a different grid value, then by calculating and comparing the grid value distribution histogram of different data sets, we can gain some information about the reaction progress. We can also isolate all the precipitation and then would be able to quantify the growth of magnesite grains. We can also isolate the pores, and then we'll be able to analyze the porosity evolution of the sample during the reaction. So here's a straightforward way to look at my sample, and most of the images are shown from these three angles. The blue one shows the cross-sectional area, and then a radial section is marked by this orange color, and the magenta shows a tangential view. So basically, if you imagine that we take a slice of the cup, this container here, and that would be shown as this rim on the cross-sectional view. And please feel free to interrupt if you have any questions. So here are some data of our experiment. The reaction progressed from the top to bottom. And here we see the generation of void space as reaction proceeds, and is also seen in other directions. However, if you take a look at these space, there's no precipitation. We basically just observed the dissolution of olivine. And then if we take a look at the SGC, which is a small grain container, we see development of fractures as reaction progress, which is more clear in this image. And apart from these fracture, we can also observe precipitations, which is represented by these patches, which gradually fill up the entire space and leads to the fracture. So basically, and then with the development of the reaction-induced fracture, the sample is divided into these smaller polygonal subregions, and then exposing new reaction surface for further reaction.
Do you get one of the fractures closing at 140 hours at the top there?
Well, it's less likely. It might be slightly off from the plane of other slides. Yeah.
So, what you're showing here is that things are just dissolving. The olivine's just dissolving.
Well, for this one, we think there's not just the dissolution, but also precipitation based on these observations. And there's more results proving
precipitation of quartz and magnesite.
Yep.
So can you see that in your colors? Or?
Not in this one, because for it's beyond the resolution for the microtomography technique. But we have a nanotomography, which later could prove there's definitely precipitation within this couple.
So is your fluid flowing through and leaving the system?
Well, it will be a semi-open system. So we have a regulator at the end of the pore system, and yeah. So what pressure, the pore fluid pressure is controlled by an intensifier, and there's an inlet both on the top and bottom of the sample. But we are not doing flow-through experiment. Yeah.
So it's static once you put the fluid in there. It just sits there.
Yeah. And then, if we take a look at the grid value histogram distribution of the two samples, here we can see, here are the best fit line of the actual distribution, just for clear demonstration. And what we see is that this histogram becomes flatter as time goes by, which means that basically it represents the dissolution of olivine, which is shown here. And if we take a look at the shape of this histogram, clearly in the in the LGC sample, it shows an asymmetric shape compared to the symmetric one in the SGC. So this means that in the LGC, dissolution of olivine would mainly cause a precipitation, a generation of pores with less precipitation on this rim. However, in the SGC sample, we see the dissolution of olivine while we are generating the pores and precipitation at the same time. So the idea is that for the LGC, we see mainly dissolution, while SGC, we can also see precipitations. And here's one of the movie of a grain from the SGC sample. And we see on the surface of this olivine, there's precipitation accumulating after about 30 hours. We see nucleation of magnesite. And then if we just pick out these individual magnesite and then quantify their volume, we can obtain a growth curve. So here, the y-axis is in log scale. So from the plot, it shows that the size of the magnesite continuously growing within the duration of our experiment. So we think the reaction shows no slowdown in rate based on the observation of magnesite growth. And then if we just isolate that entire grain and then calculate the volume, so we can have a plot of a volume change of the grain during the reaction, we can see in general, volume of this grain is increasing. However, there are also several drops, which could relate to the competition between the dissolution and precipitation. Basically, at the first drop, which is still at the early stage of this experiment, the dissolution is still dominant, and therefore you have this reduction in the grain volume. And then these later drops could relate to the development of fracture, which could bring the dissolution to dominant again. And then in each sample, we selected 2 regions to do porosity analysis. And here I have to mention that for the SGC sample, the subvolume 2 is closer to the outer edge of this cup wall. And then the subvolume 1 will be closer to the inner edge. And then by isolating all the pores within that subvolume, we can have a porosity evolution plot. And here we see that the initial porosity of both samples are comparable. And then for the first about 30 hours, the porosity increase, which is demonstrate the dissolution. While in the SGC sample, we start to see that the growth of the porosity plateau, which is related to the precipitation of magnesite that we see on the surface of the grain. And then, so basically, we think that this part is the porosity increase basically shows that at the beginning of the reaction, the dissolution dominated that whole process. And then, if we just take one subvolume from each sample, and we calculate a porosity distribution on one slice, and then move the slice along this whole subvolume, we can obtain, we call it a porosity profile of the subvolume. So basically the idea is that if you take a look at the porosity distribution within the sample from 0 hour to 30 hours, the porosity increases like relatively uniformly within the subvolume. However, if you take a look at the SGC, it's showing a similar trend to the LGC in the first about 30 hours. You see increase of porosity in both subvolumes. And then you start to see some contrast after we see the precipitation of magnesite. Basically, the surface where the subvolume is close to the edge of the cup, we see a continuous increase in the porosity, while the interior of the sample start to show a decrease, which means that there's more precipitation inside, which leads to this reduction in the porosity.
Is there any reason there's 2 different time scales there?
Sorry?
You're doing 30 hours for
Yeah.
the large one, but 100.
So yes, so because we are running this one at a shorter time scale, so yeah, we have not seen that precipitation yet. But with if we keep that reaction, I believe there will be a similar trend. But for the purpose of this experiment is just to show the evolution of the sample before you have a significant amount of precipitation. And then if we take a close look at the SGC sample, here's again the two subvolumes. And remember, this subvolume is closer to the outer ridge, and that one is closer to the inner. So basically, by putting them parallel, you can have basically a profile of the whole cup. And we see that on the edge of the cup, the porosity continuously increases, while the interior increase for the first 30 to 40 hours and then start to drop with the precipitation inside. And apart from the profile, we also did this 3D analysis on the porosity distribution. So we divide each subvolume into smaller cubes and then calculate the average porosity within each cube and plot them against their position. And eventually we can get a distribution of porosity within the whole subvolume. And here we can see at the beginning, well, another thing I have to mention is that the purple large sphere represents higher porosity, while the small blue sphere represents lower porosity. And we see that at the beginning of this reaction, the porosity distribution is quite random. And then we start to see some accumulation of higher porosity around this corner, where the sample is closer to the edge of the volume is close to the edge of the sample. And it's more clear in this subvolume, where we see, again, at the beginning it's quite homogeneous, and then we start to see a large accumulation of higher porosity around this corner, where it's close to the outer edge. And here's another rotating view, and we clearly see these high porosity accumulations. So based on these 3D porosity distribution analysis, we think that there's a higher porosity on the edge of the sample, while the inside is, shows a porosity decrease due to precipitation. So what this shows us is that inside the cup, there's more precipitation which leads to the reduction, while on the surface, the dissolution dominant, and therefore we have generation of porosity. And from our image, it further proves the result from the porosity analysis. And as we see, these patches inside the cup would represent the precipitation. And then the surface where porosity is high is later subject to these fracture development. So based on these observations, we proposed this mechanism for the reaction-induced fracture. Basically, the surface, because we have this special setting with larger grains inside the cup, and therefore those larger grain has a lower curvature on the surface. So for the precipitation, it will preferentially first precipitate on the surface with lower curvature, meaning that on the edge of the sample, you are more likely to precipitate on these larger grain, therefore leaving the surface relatively precipitation free. While in the interior of the sample, it's kinetically favored to just precipitate in situ in these places. And therefore, you have a contrast in the precipitation rate within the sample, basically higher on the inside and lower on the outside, which would lead to a difference in the expansion rate, meaning that the interior would expand faster compared to the surface. And this could generate tensile stress on the surface and eventually tear open the fracture on the surface. And here's a comparison of our idea with the previous idea on the crystallization force. So from the crystallization force theory, a fracture should develop at where the precipitation is most vigorous, meaning that a generation of the stress is generated by the precipitation and eventually cause the sample to burst from inside. However, based on our observation, the fracture actually develop in areas where the porosity is still high or even increasing, and there's no clear evidence of precipitation accumulation. Instead, we see more precipitation inside, which lead to the stretching on the surface that eventually lead to the development of the fractures. But apart from fracture, we also quite frequently mention the dissolution. Does that help in generating the fresh reaction surface? So after the reaction, we take out the piece from the cup wall and then did a nanotomography analysis. And as we see that that shows the difference value will be the magnesite precipitation. And these large grains are the olivine, while the pores are dark. And here from the nanotomography, we see the formation of dissolution channels on the surface, sometimes also known as the edge pit. So we think these channels could also provide additional fluid pathways for maintaining the reaction.
No quartz?
We do not see the quartz here. They may be amorphous, but from the EBFD analysis on these, they are mainly magnesite carbonate, magnesium carbonate. And here's a movie showing you one of the olivine grain. So the red phase are the pores inside the grain. And we see that some of these pores clearly penetrate inside the grain, and especially there will be two tubes here. They penetrate into the grain and sometimes even through the grain. So these could definitely provide fluid paths for the reaction. And within these tubes, we do not see any precipitation, so they are less likely clogged by the precipitation.
And what's the scale there?
So for the diameter of the tubes, they are about 0.5 micron. And so basically, these pore tubes will provide a subsurface dissolution channel that helps maintain the reaction. It can also make the sample more susceptible to later fracture by creating these weak spots through dissolution. And that brings us to the story of our porosity generation process during the olivine carbonation reaction. We think that it is a coupled process of both extension cracks and dissolution channels. On a shorter time scale, the extension cracks are really efficient in generating these cracks and then provide a fresh reaction surface. However, the dissolution can also provide additional fluid pathway, which is a significant contribution to the sustainability of the reaction on a longer time scale. So, in summary, we have observed the metamorphic crystals of magnesite continuously growing on surface of the olivine. And although the reaction is volume increasing, we also observed an increase in the porosity, and indicating it is a self-sustaining process. And the reaction-induced fracture is observed to generate porosity and maintain the fluid, the reaction progress. And it is likely resulted from the non-uniform volume expansion, which lead to the generation of tensile stress. So the dissolution channels, they also help in providing the fluid pathway and fresh reaction surface on a longer time scale. And this whole porosity generation process is a coupled mechanism of both reaction-induced fracture and dissolution channels. And we think that this experiment reveals the potential of olivine being used as a stock for the geological carbon sequestration. Now back to the question that we brought up at the beginning of this talk. So based on our observation, we think the reaction is self-sustaining. And porosity is generated by a series of processes, including both reaction-induced fracturing and dissolution channels. As for the mechanism of fracturing, we think it's generated by stretching due to the non-uniform expansion of the sample. And thank you. I'll be happy to answer any questions. Yes.
I'm curious, if you're doing this very large scale, what's the probability you will induce seismic events through the volume increases?
Well, I think it's less likely to produce really large magnitude earthquakes. Yeah. But right now we do not have a good way of exaggerating our result. But yeah. And we are just trying to provide a mechanism so we understand how the fracture can be generated for future investigation.
I have a couple of questions about the experimental setup. I'm not sure if I'm understanding correctly. So the outer sample is fine grains.
Mm-hmm.
The inner sample is like coarser grains. So
yep.
Why do you choose this configuration?
So the idea is that for the so for the cup, we want to make it an aggregate, so it's kind of like an analog to the rock, although natural rocks are much stronger. And the idea of having these coarser grains is because we have a really fine grain aggregate here, so it's really hard to quantify the growth of precipitation. And with these large grains, it will help us to see clearly how the precipitation grows and understand when exactly that happened.
But due to this configuration, it seems like the dissolved stuff would prefer to precipitate in the inner coarser grain stuff, and I think that's kind of like artificially induced this expansion fracture. I mean, if let's assume if like everything is uniform, would you still expect this kind of fracturing occur on the surface?
Well, if it's uniform, we have to look for other solutions. But basically, if you think about the natural rock, right, it's never going to be really homogeneous. You are always going to see these difference in grain size and also the mineral property. So you are likely to produce a similar contrast in the precipitation. So this could be proved by our result. But yeah, we have to further exaggerate the result. But yeah, so if you have a really uniform sample, it's less likely that we can produce these difference in the precipitation rate. But I think the crystallization force may be the solution to those situations.
Just one more question is, where does the quartz go if you never see it?
So we think, well, the quartz is either in the solution or it's, it does not show a specific crystal shape. So basically, from the precipitation, we think that's magnesite based on either the EBSD data and also the crystal shape. The quartz may also present with some amount, but they do not show, so it's mostly amorphous. Yeah.
I'm sure you did like an analysis of the final products. How much magnesite did you actually produce?
Well, we do not have a whole sample analysis on that. It's just that small piece, and we only deduce it from the nanotomography images. Well, it would definitely be, yeah, a good suggestion of calculating them. Yes.
I'm curious, how do you supply CO2 into the system? Is it possible that CO2 is limiting the degree of magnesite formation?
Well, if you take a look at the size of our sample, it's quite small. This is it's less than 2 millimeter. So we think we definitely provide enough fluid for further reaction. And if you take a look at the sample setting, basically we have these pore fluid inlet outlet on both ends of the sample. So it's controlled by the intensifier, which if people are doing rock mechanics, they will know it better. So basically we have a large tank that's like much larger compared to your size of sample. So you definitely have enough solution for your reaction.
And do you have pH in the system solution?
We do not, because those fluids were reacted at 200 degrees Celsius. And when we take it out, the temperature also changed, so you can never really get the specific pH at that reaction condition.
But your fluid's some kind of initial mixture of H2O and carbonic acid or something? Or
Yeah, but we use sodium bicarbonate as a buffer. So basically, the solution is sodium bicarbonate saturated solution.
It's saturated with sodium bicarbonate?
Yep.
Okay.
So would your scheme be to dissolve the carbon dioxide into something first to inject it, or you directly think this would actually be injectable?
Well, for these industrial applications, I think there are ways. So basically, we pressurize the CO2 into these until it reaches this called supercritical state. Basically, it can flow like a water, but still contain enough carbon dioxide. So yeah, and I think that might be a good way to inject the CO2. And right now, there are these tests run in Iceland, and what they use is they use these saline water and basically dissolve as much CO2 as you can in those solution and then inject it. Yeah. And one thing about the supercritical CO2 is that you have to have enough pressure to keep those as a condition.
The crushed olivine, that's a natural olivine, and the outside is a synthetic one?
So they are all natural olivines. It's just the cup is synthetic. So they are natural St. olivine, which is 91% of the first right.
So let's thank Tiange once more and thank you.